Let's now have some tutorials on Faraday's law. Our focus will be to solve problems based on Faraday's law. This is our first question. We have a bar magnet that is suspended on a spring, and it is made to oscillate up and down within a solenoid that is provided here. The solenoid is connected to a sensitive millivoltmeter. We are expected to describe and explain the behavior of the millivoltmeter, and then we are also to brainstorm and come out with any change that will cause the deflection to be greater. So let's take the first one. If the magnet oscillates up and down, then it is introducing a varying magnetic field into the coil, and that will cause a varying voltage that is induced through the coil, causing the galvanometer or the millivoltmeter to deflect left and right repeatedly as it oscillates. As it moves down, the induced EMF will cause this one to deflect in one direction, either this way or the other way. Then as it goes up, it will cause it to deflect in the opposite direction, opposite to the direction of the deflection when it was going down. So that's what is going to happen. We don't know the polarities, otherwise we could use the hand rules to determine which way will cause positive reading and which way will cause the negative reading. Okay, so we move on to the second part of the question. How are we going to make the deflection very great or greater? Keep this point in mind. Increasing deflection means increasing the induced EMF or the induced current. And we can do so. I've forgotten to write. Let me see if I can write it here. So Faraday's law tells us that we can have change in phi, that's the magnetic field, with change in time. Yeah, so if we make I could make the phi this side, this whole thing, I could make it BA. So the flux here is BA. So if the magnetic field is stronger, then the induced EMF is going to be stronger. So we can, one way is to make the magnetic field stronger. Then we can also increase the deflection by increasing the number of turns, the number of turns here. So we just have to make n greater. Instead of 500 or something, we can make it 1000, 1500, whatever. Then it will make the induced EMF greater. Another way of increasing the induced EMF or increasing the deflection on the voltmeter or the millivoltmeter will be to increase the area of the coil. In theory, that will be true, but in practice, it's going to be difficult. Then the last one I would like to talk to you about is to cause the change to happen within a very short time. In other words, let the oscillation happen very fast. So if the oscillation happens very fast, then the change in magnetic field is going to be within a short time period. Thus, it's going to be fast. If it is fast, then the denominator will be small, causing the whole quotient to be large. In other words, there will be a large EMF that is induced. So these four ways are the means by which we can make the induced EMF greater. So this is our second question. The magnitude of a magnetic field is changing at the rate of 0.02 Tesla per second. A conducting loop with area 120 centimeter squared is placed in the changing field such that its plane is 60 degrees to the field. Our tasks are to determine the magnitude of the EMF induced and also to calculate the current that flows through the loop if its resistance were 10 ohm. So go through quickly, and you may want to try it before you continue the video. Just give it a pause, try it yourself, and continue the video. Alright, so here we are. The first thing to do will be to state Faraday's law. Make sure you include all the variables that are provided in the question so that you can solve it easily. In the question, we are told the loop has only one coil. We have a conducting loop that tells us that the number of turns will be 1. Then we have the area given here, 120 centimeter squared. That one converted to a meter squared will leave us with 0.012 meter squared. Then we are told about the angle of the plane. In this particular case, you have to be very, very careful. I've been emphasizing this. If you go to Faraday's law, this angle here is the angle the area vector, which is in this direction, makes with the direction of the field. It is not the angle between, it is not the angle between the plane. This one is the angle, the line on the plane. And then the angle between the line on the plane and the magnetic field will be this. This one is, we are told, is 60 degrees. But what we are actually looking for in order to make our calculation here is indeed the angle between the magnetic field and the area vector. A vector that is perpendicular to the area. And if we have this one to be 90 degrees here, and this side alone is 60, then we expect this side to be 30. This is what we are looking for. You have to be very, very careful. Listen to the question and make sure you find the angle between the magnetic field and the area vector, not the surface of the area. Alright, so we are looking for 30. That's what we have here. Then the next thing will be to determine, look at this one. This one, we are being told the magnetic field is changing at a rate of, so the rate by which the magnetic field is changing is provided here already. All that we need to do now is to substitute everything as we have provided them here. N is 1, B 0.02 Tesla. We have cos 30 here, and we have the area here. We multiply everything together, we negate it, and we have our answer here. So it's the magnitude that we are looking for. So negative or no negative, that's not a big deal. We are looking for the magnitude. So the magnitude will be 21 millivolts. You can work it out again for yourself and confirm. The second part of our question. We have an induced EMF of 21 millivolts. And we are told the resistance is 10 ohm. So go ahead and then confirm that the current that will be flowing will be 2.1 milliamp. This is our third tutorial question. There is a coil and it has a radius. Be careful. This one is the radius of the coil, and it contains 500 turns. is placed in a uniform magnetic field. Uniform in the sense that the magnetic field lines are parallel, but the strength or the magnetic field strength is changing according to this formula. It is dependent on time. So depending on the time, we will be able to calculate the strength of the magnetic field. It is uniform in the sense that it is parallel. The lines are evenly spaced. The coil is connected to a resistor and its plane is perpendicular to the magnetic field. We are told the plane of the coil is perpendicular to the magnetic field, meaning the angle between the area vector and the field is 0. Okay. You can ignore the resistance of the coil. Find the magnitude of the induced EMF in the coil at the instant of time t equals 2 seconds. Let's see how we are going to handle that. Again, we invoke Faraday's law, and we need the number of turns, which is 500. We need the area. Calculate it yourself, and you should find out that it is something like this. Then we need the angle. I've told you already, the angle will be 0, and we are going to differentiate the strength of the magnetic field with respect to time. If any of you has difficulty differentiating, please make sure you contact me or you contact somebody to refresh your memories on differentiation. So if we differentiate, yeah, I'm not going through it. Just go confirm for yourself how differentiating this one with respect to time gives you this. We are differentiating the whole of this with respect to time, and we are going to get this. Now, we are expected to calculate the induced EMF at the time of 2 seconds. So at 2 seconds, the rate of change of the magnetic field will be 2 seconds here, making it 6 multiplied by 13, giving us this one will give us 8. So 2 cube will give us 8 multiplied by 13 gives us, and added to 0.12 gives us the whole of this one here. Okay. So invoking Faraday's law, the n is constant, area is constant, and the angle is also constant. We bring them out, then we multiply by the rate of change of magnetic field. So if we substitute everything, 500 n, area is this, cos theta, cos 0, then we have our changing magnetic field. If we multiply everything together, then we are going to get 26.03 volts. Our last tutorial question. So we have the flux that is varying with time according to this graph. So at the beginning of the time, the magnetic flux was not changing. Then at this point, it started changing. Then at that point, it started reducing to 0. So we are expected to draw the corresponding EMF that will be induced. That will be induced in the coil placed in the field of the magnetic field that is causing this flux. So we are supposed to draw it at each point in time or each range in time. How are we going to handle this? We are going to use the same approach. Faraday is telling us that if the flux changes, that's when we are going to have induced EMF. But here, we don't have the flux changing. If it's not changing, then there is no EMF induced. It remains 0. Starting from this point, the flux was changing steadily. And if it's changing steadily, then we are going to have a steady EMF induced. Compared to this side, we have the flux reducing this time around. If it is reducing, then we are going to have a positive EMF induced. Let me come back to this side. This side, we have the flux changing positively. It is increasing from a certain value, going to a higher value. In that case, Faraday's law is telling us that it will be the negative of the change. So we are going to have a negative EMF induced. Then if the flux is changing negatively, thus it's changing from a higher value to a lower value, then we are going to have a positive EMF induced. Another important feature that you need to take a note of is that the magnitude of this one is smaller than the magnitude here. You see, this one is going far. The reason being that this one is changing twice as this change, even though it is reducing, but the change is twice as this change by over the same period of time. So the rate of change in this range is higher than the rate of change in this range. This one is shorter, but it is negative. This one is bigger, but it is positive. So this is all that you need to know. Think about this and then ask questions, and I hope you understand. Thank you.